Hi, Brian.
Hello.
Again, congratulations for the Berry Prize.
Thank you very much.
I read from the Berry Prize. It says that you have done pioneering work in number theory, most notably in connection to the general Taniyama-Shimura-Weil conjecture. He has also been an important voice for maintaining rigor in mathematics education, particularly so in the recent debates concerning California's mathematical framework. Let's start with the first part of the
Yeah.
citation.
Okay.
Tell me a little bit about
Yeah.
what you
So
think
so
that we
maybe
have.
maybe I'll try to give a rough sense of maybe a couple of things that I did. So maybe I should take a step back. In number theory, we're generally trying to understand whole number or fractional solutions to equations, usually equations in two or more variables, so quite different from what usually you see in high school. Um, and one tool that often gets used is divisibility. So just a very classic example would be there's something called the Legendre three-square theorem, which describes which whole numbers are a sum of three perfect squares. So like, for example, 59 is 49 plus 9 plus 1, for example, whereas 63 is not a sum of three perfect squares. And and this theorem says, for example, like an odd number, an odd whole number, is a sum of three squares as long as it does not leave a remainder of 7 when you try to divide it by 8. Okay? So there are many situations in number theory when we try to analyze if an equation in two or more unknowns has whole number of fractional solutions, and it's found to be very useful to analyze these questions by focusing on how they relate to divisibility properties of the variables involved or some of the quantities in the equation. And we refer to this as modular arithmetic. We may be studying remainders when you divide by 8, or remainders when you divide by some other prime. And when we take a question about whole numbers and turn it into this world of modular arithmetic, it takes the problem involving infinitely many integers into a very finite number system. So it turns out to be a very tractable way to try to find obstacles to whole number solutions to equations. And this idea of modular arithmetic was actually initiated by Gauss when he wrote this famous book that kind of spawned modern number theory, Disquisitiones Arithmeticae. And so we found in analyzing questions in number theory that if we take the original problem and recast it in terms of this world of what we call modular arithmetic, it can give us obstructions to the solvability, but it can also sometimes give us criteria that may be sufficient for the existence of the solutions that we're looking for. And Gauss studied this in a certain realm of cases, but a situation that number theorists have studied a lot in the last 50 years are a special class of two variable equations called elliptic curves. And elliptic curves are roughly equations of the form y squared equals a cubic polynomial in x, like y squared equals x cubed minus 2, or something like that. And these may sound quite special, but they turn out to have a lot of interesting structure and to be a very good testing ground for many general conjectures in number theory. And when we try to study these special cubic equations called elliptic curves, even though they're not ellipses, it turns out that once again, if we want to understand the totality of the whole number or fractional solutions to these equations, points on these curves with whole number coordinates, we can introduce considerations in modular arithmetic. We can study both sides of the equation when we look at remainders when you try to divide by different primes. And when you try to assemble this modular arithmetic information, you get an infinite sequence of numbers, and we assemble those into a single function called the elliptic curve L function. It's kind of like in calculus, we may have a power series that assembles the infinitely many coefficients into a single function. Starting from an elliptic curve equation, we can introduce its working modulo a prime, study the divisibility properties of the equation when you look at remainders modulo all the different primes, and you can assemble all that modular arithmetic information into this single elliptic curve L function. And there are many conjectures about these L functions. But the most basic thing you need to know, one needs to establish to study the more difficult conjectures, many of which are wide open, is a property that we call entirety or entireness. And this is a special property that people didn't know how to solve for a long time, how to establish. And when Wiles solved Fermat's last theorem, the key point to what he did was to come up with a novel criterion to justify that the L function associated to an elliptic curve has this special property of entireness. And he was able to establish this for enough elliptic curves to solve Fermat's last theorem, but the question remained open for all elliptic curves. And that was what, together with Richard Taylor and Christoph Breuil and Fred Diamond, that was what we extended Wiles's method to handle all elliptic curves. And I should say, earlier this year, these same techniques that were initiated by Wiles, they've now been extended to some two-dimensional geometric objects, certain kinds of special surfaces. So these techniques that have been developed have kept being generalized and extended to more and more situations. It's become a quite powerful technique within number theory. Maybe one other thing I'll just briefly mention is something I did in more recent years, again, connecting back to this modular arithmetic idea, is so there's a very powerful analogy in number theory that we call the Rosetta Stone, going back to a letter that Andre Weil wrote to his philosopher sister Simone Weil in the 1940s, that in number theory, we want to study questions about whole numbers and fractions, but there are these very interesting analogies between numbers and polynomials. So like a prime number may correspond to an irreducible polynomial, or a fraction, like 5/3, may be somewhat analogous to like a rational function. In any event, under this analogy between numbers and polynomials, we sort of have a bridge. We have, or we may regard it as a Rosetta Stone, that there are certain concepts and results on one side, and you try to formulate the analog on the other side. And sometimes on this other side related to polynomials, we may have more geometric insight into what's going on, and that can suggest useful ideas. In any event, something we try to do a lot in number theory is find more and more instances of this Rosetta Stone. That can we take a problem we don't know how to study on one side, translate it to the other side and make progress, or even just develop the corresponding analogy on the other side to give us more confidence in the value of this Rosetta Stone that we use to inspire algebraic ideas coming from geometry. In any event, so the reason I bring this up is in the past, I would say in the past 10 years, together with Gopal Prasad and Ofer Gaber, we developed a new theory of continuous symmetry on the function field side of the Rosetta Stone, what we call pseudo-reductive groups. And these are sort of analogs on one side of this number theory dictionary to the very highly developed theory of what are called arithmetic Lie groups that have been studied a lot in for studying systems of equations that have a lot of symmetry in the context of ordinary numbers. And so we developed a kind of parallel theory of continuous symmetry on the other side of this Rosetta Stone, and it led to a variety of nice finiteness theorems and other results that are sort of parallel to what was known on the other side. But anyway, so we established that, and that has led to a variety of other developments in this study of symmetry in a somewhat non-classical setting.
It's at least I could understand a little bit of what you are saying. So that was an excellent explanation. I saw connected with this Rosetta Stone. I saw that there was today was announced a breakthrough prize for a guy
Yes.
who did the geometric Landrats program. So that sort
Right.
of fits in the
So,
same.
so yeah, so in fact, so I would say, right, so right, within number theory, so the Langlands program tries to establish, again, a kind of bridge between very different looking kinds of structures, and to try to take problems in one setting and transform them into some other one where you have more structure to grab onto. And it's true that in the Langlands program, there was one side of it, you might say the more classical side, where there has been some progress, Wiles's work and others, but there many things were unknown. And on this other side of the Rosetta Stone, which is much closer to geometry,
And it's
Drinfeld and
easier.
Valensin, sorry,
It's easier, I presume. It's easier.
I would say it's different. You're absolutely correct that the availability of additional geometric tools definitely makes certain concepts more tractable than they are on the more classical side. On the other hand, what's I think more important is it can motivate what type of geometric structure to then search for on the
I
classical
understand.
side.
Right.
And so, for example, an instance of this is, I would say, in the last several years, the work of Peter Scholze and Laurent Fargue on what's called the geometrized local language program. They took ideas inspired by this geometric side, and they figured out how to build the right kinds of structures in the context of what's called the classical local language correspondence. And it's led to tremendous advances there. But people never would have known what to look for if they didn't have the experience on this other side. So you're correct that the availability of extra geometric tools does sometimes lead to greater progress on this side, but nonetheless, it can also inspire the search what kinds of concepts and structures to look for. So it has been more than just a kind of analogy. It's actually inspired people to find the right kinds of ideas on the classical side as well, which is at least has led to some advances there too.
And it's really fascinating. Thanks a lot. I mean, I really appreciate myself, and I'm sure that the people who would listen to this would also enjoy. Okay, so let's go to the second part of your Barry Prize, which is concerns the Californian mathematical framework. So the recent debates that had to do with it, and I know that you became very involved and
Yeah.
you had a very positive impact on developments. And I'd like to know what is the situation? How did you get involved, and what is the
Right.
situation today?
So yeah, so my father has been a high school math teacher for all of his career. So I think I probably had somewhat more awareness about like things happening in the high schools maybe than many professional mathematicians. But I would say in 2021 I began hearing. Maybe I should take one step back. So I've been in my department. I've also, in addition to being a professor in the department, I've been the director of undergraduate studies for math at Stanford for roughly the past 10 plus years. And in that role, I've spoken with colleagues across many other quantitative fields, statistics, computer science, biology, and so on. So I had some sort of awareness of in what ways do the math topics that many students learn in this department play into what they need for their work in other subjects? And correspondingly, what sorts of tools that students are learning in high school really still get used in many of these other fields. And so in 2021, I began reading in the news about proposals to essentially remove large chunks from the conventional math curriculum under the claim that this would allow replacing obsolete Sputnik era topics with more contemporary things such as data science. And so there are a lot of these buzzwords that were being used, which could have superficially sounded very plausible in the sense that if parents don't know where the material in the curriculum goes after high school, it could be very plausible to people that maybe a lot of those math topics have become obsolete. But and I know that actually a lot of the core material in the conventional high school curriculum is absolutely foundational for modern science and frankly, even modern data science, right? So even though calculus was developed for physics, of course, nowadays calculus is used for optimization, trigonometry is used in video games, all these recommender systems, AI, all of these things rely crucially on a large part of the usual algebra and calculus and such material that's taught in the high schools and early courses in college. In any event, so seeing these claims being made in the media that I recognized as being quite misleading, I've decided that because of my position as the director of undergraduate studies at this particular university, I felt that if I would speak up, I could potentially have a positive impact on how the public debate would go around these topics and hopefully have a useful effect on making improvements to the proposals that were being made. And so, therefore, I sat down and read the entirety of the proposed 1,000-page framework document and documented what were the concerns and also suggestions for how to improve things. And so I worked, of course, together with some other people. And so in the end, I feel that what happened in California did avert what could have been a very problematic development of both gutting the university admission standards for what kids need to know for a solid 4-year quantitative degree, but also averted the problem of potentially having the high school curriculum replace substantive math content with fluff. And so I think one very useful thing that came out of the entire discussion that was had is to bring to wider public awareness the fact that indeed we do need to provide kids with a sense of how what they're being taught in school does pertain to contemporary things, right? That we're not just teaching them old material for the sake of, learning it for itself, but rather for them to see that these topics that you and I recognize as central to mathematics really do still remain the core for what people need to get a meaningful college degree in many quantitative fields, whether it's statistics, computer science, AI, data science, and so on. In any event, so through that, I think we did have a partially positive effect in California in the sense that many of the problematic proposals were, in fact, eventually toned down a lot. So, although in the end, I don't think the California math framework necessarily achieved as much as it could have, I think a lot of the big concerns were largely addressed in the final version. On the other hand, these things moved on to other states. So, for example, after the attempts to water down the high school curriculum in California did not pan out and were able to be blocked, again, through the efforts of many other people, not just myself. In Connecticut, a similar thing arose where there was an attempt to try to get the public university, University of Connecticut, to water down the math requirements for college admissions. And that was, again, presented under a kind of argument of making things more accessible. But in fact, the effect of watering down the math requirements for college admissions would really have the effect of making quantitative degrees out of reach for the students who don't learn what they should have been learning in high school. In any event, many parents got involved in Connecticut. I spoke to people there, provided them with information, and so they were able to stop the proposal there from getting very far. So fortunately, in Connecticut, things are now sort of in a reasonable state. But anyway, things have been occurring in other states, and I think the main takeaway lesson from this is that there's a lot of value that can be had by both not just professional mathematicians, but also people in other quantitative fields, computer science, statistics, also business and industry, getting involved in these discussions to enable both parents and school districts and the people who set the curriculum to appreciate ways in which the content of the curriculum really does still remain as relevant now as it did long ago.
Yes, so I understand. So in the end, you are saying that you were able to influence the debate and you made corrections, but you are not entirely satisfied. So what? Why?
Well,
He was.
I so just as an example, so as I said, there's certainly ample room for improving the material that the teachers get in the high schools with which they can help kids to see the value of what they're teaching in the room in the classrooms. For example, enabling kids to perhaps see that, as I mentioned, like trigonometry getting used in video games, for example, right? Or maybe some inequality ideas being connected to probability and other things. And and I think that if the process by which the textbook approvals had incorporated a requirement that the publishers provide more indications of contemporary relevance, then that would be very useful to the teachers when they're trying to help the kids to get more motivated to learn the material in the curriculum. But unfortunately, that was not able to be included, for example. So I do think that there is a lot of room for helping the teachers to see the contemporary relevance so that they can convey that to their students. Because of course, look, even when you or I, learn about a piece of, advanced mathematics, we're also driven by motivation, right? We see its value to do something that we find interesting. And I think quite reasonably, many kids or their parents in the high schools can feel similarly, like, why are they learning certain topics? And so I think if publishers could do more to help teachers to show kids these examples of contemporary relevance, it could help a lot to motivate them to persist in getting through the material that they may find initially quite challenging in the high schools.
Yes, indeed. I certainly sympathize with everything you are saying. How do you, what do you perceive as being the main challenges that you are facing now? I mean, are you interested in other issues concerning education or
Well,
any
I
other?
would say, I mean, on the education side, I think the main challenge is that the way that, at least for math, the way that math is used tends to be under the hood. And so it can be very easy for people to fall into the mistaken belief that because of the ubiquity of computers, that people don't need to understand some of these, perhaps difficult mathematical ideas because computers can somehow take care of everything. And we would never apply that principle to reading, because there are spell checkers and because AI can write essays, therefore people don't need to know how to read anymore. Like nobody would make that argument. But something roughly of that nature is being made about math in various places. And to be fair, some of the people making these arguments may just be genuinely misinformed. But in any event, so I think one of the big challenges is to enable more people to see, to kind of open up the hood and look underneath and help
Particularly when
them.
it comes to AI, I mean, the extraordinary success of AI, of large language models, is completely based on optimization. I mean, it's
That's correct. Right. There's a
very
right
mathematical
probability, linear algebra.
algebra, right?
Exactly. Right. And so to people who don't know how it works, it can all seem like black magic.
Right,
But of course, the people who are going to push the developments of these things and use them wisely, they will have some awareness about what's going on under the hood. So I think that there is a lot of potential for enabling more students to see the utility of these things, but somebody has to give the teachers better material with which they can convey that. And I think that's still a huge problem. But traditionally, I think this has been one of the difficulties in with appreciating the role of mathematics in wider society. That with physics and chemistry and medicine, biology, people can see more directly how the scientific
right.
advances pertain to what people use every day. Whereas, like you and I recognize that there's all this math lying underneath, it's lurking inside the computer, but the
Right.
creation of more material to help people to see that that mathematical knowledge enables other people to develop things further would, I think, go a long way towards, well,
Yeah.
improving the reputation of mathematics, but also, as I say, enabling more kids to get the motivation that they need to persist through learning some of these more difficult topics in high school.
No, in fact, it's pretty clear that the range of mathematical applications has increased dramatically in
Right. Yeah, cryptography. I mean, there are
anything that
many,
uses
many of
modern
these things.
technology. It's
Yeah,
just
absolutely.
incredible. The
Yeah.
mathematics, I mean, the applications of mathematics are all over the
Right.
place.
But as I say, it's kind of it tends to be
Under the hood, as you
out of view. Right.
yes,
And
yeah,
and
that's
and I
correct.
think that as I say, if we could enable more people to see where it's lurking there, and give kids some kind of activities or something which enables them to make direct contact
Right.
between what they're learning and those applications, even if in a very toy model, it probably would help a lot. And you know, hopefully, I mean, there are organizations working on that sort of thing. There's an organization in Texas called Skew the Script, which tries to create such material. But in any event, I think that's one big loose end from a lot of this, which could help. And I think it's something whose awareness in the wider society still has a lot of improvement to be made.
Yeah, indeed. Well, thanks a lot. This was extremely useful. And I mean, I wish you that you continue to have success both as a mathematician and as an intellectual involved in various issues, most importantly, education, mathematical education, of course.
Yeah. Thank
Uh,
you very much.
well, thanks, Ryan, and all the best.
Thank you.